Hello everyone, welcome to this Physics 1 course. This is a supplemental course to help you learn a little bit more. Um, Assuming you know some kind of calculus, but if you don't, that's okay. What we're going to be doing is just for the derivations using the calculus, maybe one or two questions. If you are solely in algebra or trig based, then don't worry about it, you won't need it. So, this is Physics 1. And we're going to jump right in. And the first unit in physics is a concept called vectors. So, what is a vector? You might know him from Despicable Me. This guy here, vector. And he says that a vector has direction and magnitude. Oh yeah. So, direction and magnitude. Meaning that you have to have some kind of value, like 1, or 2, or 3, or 4, or 5, or 6, or something, and a direction. So, to the north, to the south, at 20 degrees, etc. You have to have some kind of value and some direction. That is literally the definition of a vector. So, yes, vector from Despicable Me does in fact have it correct. So let's look a little bit more mathematical stuff. So, let's say you're driving down a road, and you look at your speedometer and it says you're going 200 miles an hour. First off, you will probably crash, but is this a vector? The answer is no. This is not a vector, and the reason why is because you only have a magnitude, but you don't have a direction. There's no direction assigned to this. This is called a speed, when you only have the magnitude of your velocity vector. But this is not a vector because there is no direction. So no direction. Let's look down here. Let's say that you instead have somebody telling you, a GPS or something, saying you're going east. Is this a vector? Yes, this is a vector. You're going 200 miles an hour to the east. This is now has some kind of encoded information that gives you a magnitude and direction. So let's go a little more fun now. Let's go a little more intensive with it. So, let's say we have a coordinate system up here, which shows north going up, west to the left, south to the bottom, and east to the right. And we're still driving 200 miles an hour. We're going to the east. And if you look, the arrow points to the right, right? You see that. The arrow goes to the right. This is how we describe a vector. We say we have some kind of arrow, and we show it going in some direction. So in this coordinate system, we show it going only to the east, only in one direction, only the east. It has no components, they're called, to the north, or to the south, or to the west. It is solely going in the east. So, what if we're going that same 200 miles an hour, but now we're going 45 degrees. This would be north of east. So this would be 45 degrees north of east. What do we do? Well, this is still a vector. We're still going 200 miles an hour, and we have a direction. The direction is 45 degrees north of east. It says there 45 degrees. So this is still a vector. And what we can do is we can actually resolve this into components, because you can't really get too much information out of this when you just have the vector line. What you should probably want to do is break this up into vector components going in the north and in the east. So how do we do that? Let's take a look at our trig again. So we're looking at trig, right? SOHCAHTOA, our favorite friend. Sine of theta is equal to the opposite over the hypotenuse. Cosine is equal to the adjacent over the hypotenuse. And tangent is equal to the opposite over the adjacent. These are all functions of theta. So, this is basically the way that we're going to be able to use to describe a vector. And something to always remember is that the hypotenuse is always the vector. H is always the vector. So, whenever we're talking about a vector, the hypotenuse is the vector itself. So, for instance, if we're looking for, if we come back here to this triangle again, that this is still 45 degrees, going 200 miles an hour, north of east. If we come back to this, and we want to find out how many miles an hour we're going to the north, and how many miles an hour we're going to the east, we have to break this up using SOHCAHTOA. So, this side here is the opposite side of the triangle. This side here is the adjacent side of the triangle. So, if I want to know how much we're going to the east, we're going to say that it's the adjacent side. So we're looking for the cosine, right? So so cosine of the angle is equal to the adjacent side divided by the hypotenuse. Well, we can do a little bit of algebra here, and we have hypotenuse times cosine of the angle is equal to the adjacent leg, which is this portion here. This is how much is in this direction, going in that direction. So we plug in our values. We have 200 cosine 45 is equal to the amount in the east. Now let's do the same thing for the amount going in the north. Well, this is the opposite side of the triangle. So if that's the opposite side of the triangle, we're going to be looking for sine, because sine theta is equal to opposite over hypotenuse. Moving this over here again, we have 200 sine 45 is equal to the amount in the west. These here are component forms. They're called component forms of the vector. They tell me how much it's going in one direction, how much it's going in the other direction. And this is what's going to basically lay the framework for the entirety of the rest of physics. So now let's talk about something called the displacement vector. So let's say you're standing right here, and you go here. You have covered a distance of 20 meters. You have displaced a distance of 20 meters. Simple enough. Let's talk about something like this now. Let's say you're starting off at this position, and you walk 20 meters to the right. You stand here for a second, maybe drink a sip of water, and then you walk 20 meters up, and you end up here. What's your displacement vector? How far did you travel? Or what is your displaced amount that you traveled? Well, it's not going to be 20 plus 20. It's not going to be 40. So no, not 40. It is going to be the distance from here to here. It is this green arrow that is our displacement vector. That is how far we've displaced. So how do we solve for that? Well, using Pythagorean's theorem, we know that 20 squared, well, we know that a squared plus b squared is equal to c squared. A is 20 squared plus b is 20 squared. That's equal to c squared. So we have c is equal to the square root of 20 squared plus 20 squared. And that's pretty much your final answer right there, unless you want to continue to evaluate that further. So let's go and talk about this. How far have you displaced from here? Now this is a bit of an interesting one, because you have some height here, you have a distance going like that, right? We just said this is what the displacement vector would look like, this big vector here. So we know you're going 20 in that direction, and you're going a little bit more extra in that direction, right? And then you go up. So does this look something like that right triangle we were talking about before? It does, except we need to add on this amount here, this 20 meters, plus whatever this portion is for that a squared portion. So let's do it. How do we do it? We see there's a 45-degree thing here. There's a 45-degree angle. So we can solve for this portion by, again, doing, this is the adjacent leg, so this is cosine of the angle 45 is equal to the adjacent over the hypotenuse. The hypotenuse is 20, so it'll be 20 cosine 45 is equal to the adjacent leg. So we know that the total a squared, or we know the total a value is going to be 20 plus 20 cosine 45. Now let's talk about how high it travels. Well, this here we say is the opposite, right? So this is sine 45 is equal to the opposite over the hypotenuse. Well, this is a 20 again, so it'd be 20 sine 45. And that's how high it travels. That's equal to, that's equal to O. And that's our B. B is equal to 20 sine 45. And that's because it travels only 20 sine 45 up from this position, and it travels 20 total plus 20 cosine 45 all in this rightward direction. That's how we get this displacement vector here of doing a squared plus b squared, so it'll be 20 plus 20 cosine 45 squared plus 20 sine 45 squared. And it'll be the square root of that. That's equal to our displacement vector. Sorry, that is the displacement vector. All right, so now let's talk about how do you add vectors together? We add them from base to tip. So we have this a vector here, and we have this b vector here. To add them together, you literally just go from the base of the first vector of the a to the tip of the b vector, and you draw a line, just like we've done here. This is a plus b. So let's practice what we just learned. So we have three vectors here, right? And three different angles. This thing wants to know in what quadrant is a plus b plus c. Now, how do you solve them? Well, you could, if you wanted to, line them up and figure it out from there, which I think is a pretty good solution here for something quick and easy if you had the ability to do this. So we could do that here and then figure it out from there, just like we said before. I guess not. Nevertheless, we would have something like this, and then some kind of drop down like that. That's a good way to solve for it quickly without doing any analytical stuff. But the better way to do it is to add up the components. So we add up how much it is in this x, how much it is in the y. So how much is in the x here, how much is in the y, plus how much in the y here, how much in the x, how much in the y, how much in the x. And we can check and see where that displacement vector or that addition will put us at. So let's do that. So we know that for a, the amount that it climbs. So one more thing before we start doing this. We can only add vectors that are in the same plane. So what I mean by that is you cannot add x plus y. You cannot add this red with the black down here. You cannot add them. They are completely in different planes. They cannot talk to each other. They cannot see each other. They don't know what's going on. The only way you can add vectors is by adding their components. So you can add all the reds together and all the blacks together. But, sorry, I messed that up. You can add all the reds together and all the blacks together because they are all on the same plane. So let's try this. So this is in adjacent. This is an opposite leg. So as we discussed before, this would be a sine of theta a. And we know that this b is going up, right? So it'll be plus b sine theta b. And now look at this. This one here is going down. So it would be minus c cosine, because this is an adjacent leg, right? This is adjacent to that angle, cosine theta c. And that's going to give us how much we are in our negative y direction, we would call it, in the y direction. And now we're going to do the same thing for the a direction. So we have a cosine theta b plus b sine theta b. Or this would actually be minus b sine theta b. And that's because b is pointing in the opposite direction of a, right? A is going that way, b is going that way. And it would be minus c sine theta c, because it's going in the same opposite direction that way. And we're all defining this as this way being positive, and being the right way being positive, and up being positive. That's called the standard coordinate axis. So that's how we'd be able to solve for where they land. Now, if it's asking what's the magnitude of a plus b plus c, well, this is what we just did. We just solved for it. This will give us exactly how much is in the y, how much is in the x. Once we solve for how much is in the y, how much is in the x, we use something called the magnitude equation, which, when you think about it, is just Pythagoras' theorem. And the reason why is because, again, we said that the hypotenuse is always the vector, right? So this tells us how much is in the x, and this tells us how much is in the y. So all we would do is x squared plus y squared, and we do the square root of that, because that gives us h. That gives us what we want to know. That gives us the magnitude of h. So let's take a look here. If we were to evaluate this, we would get some numbers for x, which we can plug in here. This is x. We get some numbers for x, which we would be able to snake in there, and some numbers for y that we plug into here. And that would give us the value that we're looking for. So if we wanted to fully expand on this, we'd have something like the square root of a sine theta b plus b sine theta b, yeah, so this would be a sine theta a, b sine theta b, minus c sine theta c, all this squared, plus, and then the same thing in the x direction. So a cosine theta b, theta a, plus b, that would be minus b. So minus b, this should be, we said it was sine theta b, and it would be minus c sine theta c. Sine theta c. And this would all be squared. And that would tell you the magnitude. So, what if we were going to do negative a plus 2b plus c? Well, we know a, right? A is this vector here that we know what it is. We know that in the x direction, so ax, so this is how we write vectors when we're breaking them up. We say ax and ay. So we know ax is going to be a cosine theta b, theta a. And we know ay is going to be a sine theta a. And again, this is because the vector looks like that. This here is the angle theta a, and we are looking for, this is ax and this is ay. So if we want to make it negative, that means that the x direction has to point negative and the y direction has to point negative. So all we're going to do is add a negative sign in front. Now we want to do b, right? bx, by. So b goes in the opposite direction. So it would be b cosine theta b and b sine theta b. And with that, I want to multiply these by 2. But I want to multiply the resultant vector by 2. So that means that both of these would have to be multiplied by 2. Now, c, we just leave c alone, but we can resolve it as well here. So for cx, we have c, that would be c sine theta c, c cosine theta c. And now you're probably wondering, why? Well, because the vector points this way, right? The x direction is this down here. The y direction is this. And if this is our angle, that means that the adjacent is now the y, and the opposite is now the x. So don't just rely on it being always cosine or sine. Draw it out and figure it out from there. Now, you can only add vector components. Remember that. You can only add vector components. You cannot add the whole vector itself unless you're doing it drawing. You can draw added vectors together, but you cannot do it mathematically. The x and the y planes, x, y, and z planes cannot see each other. They cannot see each other. You have to add up their components. So, let's talk about an airplane. an airplane we have here flying through the air, and it has a velocity, which is a vector. Velocities are vector speeds, are the magnitude of the vector. And it's flying at 300 meters per second to the left. So there's our vector total. That's what tells us it's vector. There's a headwind of 150 meters per second. What is the velocity seen from the ground? So if you're standing on the ground and you look and this airplane is flying at 300 meters this way, meters per second this way, there's a headwind blowing at 150 meters per second. How do you think we could solve this? We have two vectors going against each other. What can you do? That's right, vector addition. So we have 300 going to the left, so we say this is positive x, and this is positive y. That means that 300 is positive, and 150 is negative. So that would give us our total value of 150 meters per second to the left, because it's positive. So we know that the airplane is still moving to the left at 150 meters per second. Now, I'm going to show you the traditional vector notation and what it looks like. So in 2 dimensions, you have, this is the general xy direction. You have y going positive this way, and then x is going to the positive right. In 3 dimensions, you have x going towards you, y going to the right, and z going up. You might see these flipped sometimes, or y and z might be flipped, but typically this is the more standard convention. So what do you see vector notation from? Well, you might see an I hat. This is a little tiny thing like that attached to the number, and that tells you how much. It's the same thing as like saying the cosine or the sine. It's how much is going the x direction. J hat is how much is going the y, and k hat is how much is going in the z. So let's talk about this one, right? We're going to write this in vector notation. So how much is going in the x direction? We have 15 cosine 30 going the x, and we have 15 sine 30 going in the y. Now we can write this in vector notation by saying this is 15 cosine 30 I hat plus 15 sine 30 j hat. This is what a standard vector notation would call, and we would say this is a vector by putting a little half arrow on top of it. So this is a full arrow, this is a half arrow, and it's just, that's the vector notation. So this is what a vector notation would look like, as you can see here. So we say the amount in the x, the amount in the y, just like we did there. This is the amount in the x, this is on the y, and that's vector notation. So last quick one, we have a plane now. It's flying at 100 meters per second to the north, and there's a headwind 20 degrees south of east was the velocity of the plane relative to the ground. So let me redraw this. We have a wind going this way, and it's 25 degrees south of east, so it's 25 degrees here. And we know the airplane is going 100 meters per second in this direction. We cannot add the two vectors together like this. Remember, we have to break up the headwind here into headwind in the x and headwind in the y. So headwind in the x, how much is going in the x? Well, it says it's 15 meters per second. So in the x is this portion right here. That's the cosine. That's the adjacent. So cosine, 15 cosine, 25. And how much is going the y? That's the opposite, so it would be 15 sine 25. Now we can add up the components. The only ones we really need to add are the y direction. But we can add up the totals anyway if we want to. So we have hy going negative, right? Because we said this way is positive y. So we have hy going negative. It's going against it, right? It's dropping this way. This is the direction of hy, so it's negative hy plus 100 meters per second. That would be your total velocity. That would be the speed seen from the ground. The velocity, you'd have to assign a direction. So you could say negative hy, which would be negative 15 sine 25 plus 100. This would give you some value. You can say this value to the north, or to the top of the page. Now this is a vector. you could also say negative 15 sine 25 solely in the j hat direction is equal to the plane's velocity. And that's also your final answer. That is it for vectors and vector addition. I implore you to go try the quiz out on the Google courses. Thank you.